Okay, welcome guys. So this video, let's talk about norm space and inner product space. Okay, so it's just some very introduction video about the definition, and I want to introduce some P norm and prove some inequality. Okay. So let's say you have vector space V, and in this video we focus on only finite dimensional, right? But I mean, you can do the infinite dimensional as well. So the dimension V is n, which is finite. And the inner product space means that you have V cross V go to V, not V cross V go to F, right? So you have a vector space with some coefficient F. So usually in like the undergraduate, people you only use the real number and C, but actually it can be any coefficient field. Okay, such that if you give me two vector xx greater or equal to 0, if it's 0, then it must be 0. Okay, so this is rule first. Number one. Second one is that it must be yeah. So it depends. If you are in a complex coordinate, complex field, you can you are allowed to use this. Okay, and then which is bilinear. So yeah, bilinear. And also, yeah, it becomes like if you're usually in become this, and if you're another position, you need to do the complex conjugate. Yeah, so in this video, I would say that our rules, since we have complex conjugate, so our rules only works for I or C, right? So if you are working in a finite field, then it will not work. Okay. Yeah, so this is inner product space. Okay, and what is so let's say norm space, right? So the norm space seems as the same as inner product space, but less restricted. So basically, given a vector in a linear in a vector space, you can define a norm, right? So norm should be some field, and greater or equal to 0, right? So since it must be greater or equal to 0, right? So in a complex case, we must constrain that x to be some real number. Okay, so such that if x is 0, then it must be this, and also you need to have the triangle this, right? You need to have this triangular inequality. Okay, and the third is that if you tie some coordinates, take a norm, they become absolute value of r. So now the coefficient must be complex number or real, and it becomes this, right? So this is a standard norm. You can use the length of the vector. Okay. Yeah. So this is the definition. Okay. So let's talk about let's forget about let's say so the obvious theorem is that if you have an inner product space, let's say so you have an inner product on defined on vector space, then you can define the norm, right? So I can define norm xx to be let's say square root of xx, right? So the theorem is that at least x will be norm, will be a norm. Okay, so it's obviously this is easy because from the first theorem, from the first from this this requirement will give you this requirement, right? Because if the inner product, if the norm is 0, that means the xx is 0, but the rule says that if x is inner product 0, then x must be 0, right? So still O. And this is a triangle. This can be proved by the Cauchy-Schwarz. So I will leave the Cauchy-Schwarz inequality proof in below the in the comment, so you can check. And also this is by definition, right? By this, right? So basically, if you times, let's check it. So if I define this to be square root of, let's say, alpha x, then it become alpha bar, right? Xx. So it become alpha absolute value xx, right? Which is alpha xx. Okay, so this is a definition. So now we see that if you have so we prove what? We prove that if we have inner product space, then we can create, then it must be greater or equal to the norm space, right? Because any inner product space can be do it, so it will automatically induce a norm space. Okay, and the next thing I want to talk is the P norm. Okay, so P norm. So P norm on Rn or C, right? Okay. So P norm is a interesting thing. So P must be greater than 0. So ideally, that one can define P norm xp to be you just calculate each component and do the power P, and the sum of them and take 1/P. So the standard idea is that 2 norm, right? So the 2 norm is the Euclidean norm. So everybody learned in the high school, right? Basically, it's the length of the vector, right? So you can check that this x is indeed the norm, right? So but you need to use a inequality called the Holder inequality. So basically, Holder inequality is a triangular, basically just this. Okay? So this is a really amazing results that if you. So this is amazing inequality that you prove that your P norm must be the correct norm. Okay. Okay, so how about 1 norm, right? So 1 norm is this. 1 norm just take each absolute value, right? So just sum over xi I from 1 to n, right? So 2 norm, and also the infinite norm. So infinite norm or the maximum norm is defined to be the max of xk, right? So just take each get the maximum component. Okay, so we have the P norm. We have 2 norm and 1 norm and infinite norm. Okay, so let's finally give the inequality. So this inequality is very trivial, right? But I want to say a little bit. So inequality on P norms. So what important thing is that so I claim that if you restricted the norm on 1 or 2 or infinite norm, then that will be restricting on all of it. So for example, if I set x 1 norm to be something, right? To be something, then this second norm, right, cannot be too large, right? And the x2 norm cannot be too small. Right, so as the if you restricting the second norm, then x1 norm and infinite norm cannot be too small and too large. So I just want to say that they are basically bounded by each other. Okay, so the idea is that yeah. So let's see the proof. So let's see some interesting results. So yeah, right. So remember that your S2 norm is defined to be this, right? And your x1 norm is defined to be the sum of absolute value, and your infinite norm is to be maximum, right? Xi. Okay, so obviously is that if we use square it, right, then you can see that x2 norm is less or equal to x1 norm, right? Because if you square both sides, then there will be some positive term coming from cross product of x1, right? So trivial. And also x2 norm is sum over square, right? So sum over square, take a square, must be greater or equal to the infinite, the maximum one, right? So right. So this equality, the first this equality tell you that if you restricted the x1, right, then x2 cannot be too large. Also infinite cannot be too large. Okay. But how about the lower bound, right? So we can still get some lower bound. So let's say you take this infinite norm. It's obvious that this infinite norm take the maximum of always, right? So this maximum norm, first, well, since you only take the one component, right? So it's less than this, right? So this is already proof. But the idea is that this will greater or equal to n, right? Take a x2 norm, 1 over n, right? Okay. Then the reason is that you take average, so right. So let's maybe prove this. So you can write it as this. So maximum xi, right? So this is obviously the correct one, right? Because I can replace each term. I can replace each xi to be the maximum, then it will only increase this, right? So it will automatically. Oh, okay. Sorry, I did a stupid thing. This should be the first norm. Sorry, yeah, this should be the first norm because right, the first norm is this, right? So if I take a half, then it's obvious this will less or equal to n x infinity, right? Because I can replace each xi to be the maximum one, right? So I get this. Also, finally, if I want to show what claim is true, I need to prove that the one norm is bounded by something other, right? So the Cauchy-Schwarz tell me that one norm is actually less or equal to square root of n of 2, right? This is by Cauchy-Schwarz, right? So it's very easy. You can check out my Cauchy-Schwarz video. And also this guy is still greater than equal to. Okay, so this is the final result, right? So if I, let's say if I restricted the x1, right? If I restrict x1, then this will be restricted, right? So you see, if this is restricted, then this guy cannot be too large, this guy cannot be too small, right? So they are both bounded up above and bounded below. Also, if you restricted x2, right? If you restricted x2, then you can see that right. So x1 cannot be too small, and x1 cannot be too large, right? So they are both correlated. So if you restrict one of them, then the rest two cannot be too large or too small. Okay, so yeah, this is the norm space, and I think yeah, so that's it. I will see you guys in the next videos.